So thank you very much, everyone, for joining. This is the second session of our webinar about Xsens Analyze 2025. Today we'll be seeing the recording of our previous session, where our researchers, Domiti and Roelin, have been explaining how they created this new biomechanical update. Now we have biomechanical models for male and female. Afterwards, we will have the online Q&A session. So please put all of your questions in the questions tab that you will be able to see on the right of your screen. This session is being recorded, so don't worry if you miss a part of it, or if you want to rewatch it, or if you want to send it to someone else, you will be able to do that. We will send you an email within a few days with the recording. Thank you very much and enjoy.
Hello everybody, welcome to this webinar about our new Xsens biomechanical model, the innovations, the insight, and obviously the impact. We want to give you all a warm welcome. We're very happy to see that so many people have registered for this webinar. A little bit about Xsens, for the people who do not know, this year Xsens is actually 25 years, so we are very happy to be able to show to you today on our 25th anniversary year that we have also a new biomechanical model. Obviously, Xsens has been around for a long time, and yeah, we have a global presence, so multiple offices, over 2,000 customers that use our equipment. And today is again a next step in that journey of us that we want to do at least another 25 years. So a little what is new in MVN Analyze 2025. We try to adapt smarter workflows. Our goal obviously is to make MVN quicker, easier, and faster to use. So to do that, we did something which we call auto sensor mapping. What it does, it allows you to put the window sensors anywhere you want, left on right, right on left, and with an advanced calibration, it will exactly know where the sensors are, and hence it will basically lower your setup time. We implemented a dark mode for the people who are in darker labs and don't want to be blinded by our previous software. We have a nice dark mode, some new icons that make it easier to use. And obviously, that's why I brought Roelin and Domitil today, we have a new biomechanical model.
All right, thank you. And yeah, welcome all of you. We are very happy to present you today the new biomechanical model, the changes we made, and also the rationale behind it. However, before we dive into what's new, let's quickly revisit how we get to such accurate and reliable data in the first place. At the core of our system are inertial and magnetic measurements unit, which, as you may know, measure acceleration, linear acceleration, angular velocity, and the Earth's magnetic field. And unlike optical systems, it does not measure directly the absolute position and orientation in the global space, which brings us to two well-known challenges: the magnetic disturbance, which can degrade the heading accuracy, and of course, the integration drift. And this is why over the last decade, we've addressed these issues and limitations with a multi-layered solution, combining advanced sensor fusion algorithm with biomechanical and physical modeling to achieve magnetic immunity and drift-resistant motion tracking, even in complex, uncontrolled, or magnetically disturbed environment. And it all begins with our sensor fusion engine. Each sensor performs high-frequency signal processing using our patented strap-down integration algorithm. And these algorithms run internally at around 1 kilohertz, preserving then the motion dynamics, even when outputting data at lower rates, as you may know, with our link system at 240 hertz and the Awinda at 60 with the full body system, or at 100 hertz with the lower body. And this ensures that critical signal fidelity is then maintained and fed into our models. Our model, the biomechanical model, 23 segments, 22 joints, which are following the ISB recommendation. With 17 sensors, 17 segments are tracked directly. The remaining 6 are estimated through our engine. And to ensure high motion capture fidelity, we also incorporated a soft tissue artifact model. Indeed, the connection between the sensor and the corresponding segment is not a rigid one. as it may fluctuate depending on the amount of soft tissue movement. Hence, our sensors are modeled as loosely coupled to the bone to simulate and account for that movement. And on top of that, we have, of course, our sensor to segment calibration to map accurately our segment, our sensor to our segment. And as you may know, this is a critical step to have accurate data, as it enabled to have the initial segment orientation and to map that with our sensor. Further models, of course, layer are included, such as, well, the floor contact detection, or magnetic immunity, and also integration drift compensation. All these models, they operate in real time, enabling robust, full body 3D capture motion in a variety of movement, and so anywhere. On top of that, we also have an HD reprocessing, which leverage them the same data, but with more computational resources, enabling enhanced accuracy, particularly for complex motion, as you can see on the video with ground contact with the push-up. You see a difference between the live and the HD process and the foot contact. Altogether, this engine enabled 5K capabilities, hard to achieve. The multiple contact points, but also magnetic immunity, drift-free orientation, multiple person tracking, and a 3D position estimation. And this robust system allows us to deliver laboratory quality data in real-world field conditions. And this is the software that you know and may be familiar with. So why did we update our biomechanical model? Why did we start here? Well, our biomechanical model is one of our core technology. And right now, our legacy model, like many in the field, is built on generic anthropometric data, primarily derived from male cadaveric datasets. While this is standard practice, it presents significant limitation. When applied to an individual with different body types, like female users, systematic inaccuracies emerge and may then impact critical output, like segment properties, joint angle, segment position, orientation, balance, which then would, of course, impact the kinematics and any other analysis that you would do on top of this. And all these outputs then may also impact the objectivity of the assessment which then goes into an ergonomic, walking, but also more dynamic motion like the drop landing, or also in clinical and rehabilitation for musculoskeletal diagnosis. And we capture movements. So these anatomical particularities are important for us. These discrepancies we want to avoid. And this is why we have Biomech 2.0. And it's true that regarding body dimension, well, we already allow users to manually customize this segment length to better match individual proportion. This approach, we know, has some limitation. It can be time consuming, and it relies on anatomical landmark expertise from your side, and it also means that it's prone to user viability. And most importantly, it is regarding the body dimension, but not the properties. So inertial properties such as mass distribution, center of mass, still are based on male references. And this limitation really underscored the importance of having biomechanical models that represent both male and female anatomy, which is why we have now Biomech 2.0, a male and a female model based on living data sets. Of course, these data sets come with an average height, and then we rescale them linearly to a 170 human model, which is the one that you have now in the new software. But this is not all, because Biomech 2.0 is not only regarding anthropometric data. We also update and refine the spine model. With only 2 sensors on the spine, on the pelvis and the sternum, we use a spherical linear interpolation to estimate the motion in the untracked spinal segment. From there, we improved the model in 2 key ways. First, we updated the segment's length to accurately represent the thoracic and the lumbar proportion. Then, of course, we look at the physiological behavior. The human spine transitioned from an S to a C shape while bending. As you can see on the graph, the proportion between how much the pelvis accounts for this the thoracic and the lumbar, differs, and it differs along the bending and the flexion. This is why we refine our function in two ways. First, we adjusted the slurp weight ratio, and then we added on top of that a gradual function. All these result now in a new spine function, which is physiological, have a more physiological behavior with an S to a C shape, and then represent the well-known lumbopelvic rhythm. Today, we are very happy to introduce you, this is Biomech 2.0, the latest evolution of our motion analysis system featuring anatomy-specific male and female biomechanical models. And with Rolene, we will walk through the validation study comparing these new models against our legacy system and optical motion capture showing enhanced accuracy across a variety of tasks.
Yes, so today we'll present you the two new biomechanical models which represent male and female anatomy specifically. We will here go over the whole validation procedure as we publish in our white paper. But first, I want to explain some naming conventions we use. So at the left side you have our legacy model. This is the model you already know from our previous software versions as well, and we refer to it as BM1, Biomech 1. This one is also still available in the 2025 versions. Then on the right side, you see the new biomechanical models, a male and female version, which is called the BM2, Biomech 2. So, okay, how did we objectively assess the performance of our new models? For that, we used our MVN models against optical motion capture systems. So on one hand, we had our full body Awinda system, with 17 sensors, which runs at a frequency of 60 Hz. We measured all body dimensions, and then all body dimensions were measured also by the same person to avoid inter-operator variability. Then the body height and the foot length we used as input for the scaling of the rest of the model. After this, we did an end-post plus walk calibration with some additional checks, for example, in the inter-hand distance and the inter-feet distance to assure the quality of our calibration file. At the end, after all recordings, we did the reprocessing, used the HC reprocessing. On the other hand, we had our optical motion capture system. It was a quality system with 15 cameras, and we put 43 reflective markers according to the sports marker set. These markers were placed on top of the skin as much as possible on bony landmarks to avoid motion artifacts as much as possible. But for that, it means that we could not use our Xsens Awinda shirt and the gloves, so we taped the IMUs on top of the body. We initially started with a static A-pose recording, which helped in labeling. Then we had an anatomy-specific skilled OpenSim models, a female and male specific, which afterwards we used the inverse kinematics tools to get the joint angles. Okay, so in this validation procedure we had 11 participants, 6 male, 5 female. We asked them to perform motions which were specifically for the upper and lower body. For the upper body, these were the arm raise and clap, as you can see in the figure, and we had the spine bending. Then for the lower body, it was walking back and forth on a self-selected speed, and the subject performed squat jumps. We divided then the analysis in 3 different ways. For the upper body specifically, then the lower body, and we also did a full body analysis on body dimensions. So specifically for the upper body analysis, we had on one hand the arm raise clap motion, as you can see in the video. We extracted all clapping events, so above the head and in front of the body, and we calculated the Euclidean distance between the hands at those specific points. We calculated them for the optical system and for MVN, both the legacy models and the new one, and we calculated the error between the systems in centimeters. Then to get one overall accuracy metric, we also calculated the root mean squared error. Then on the other hand, for the upper body, we also had the spine bending. Spine bending was 2 cases. We had, first of all, the ground reaching accuracy, in which we took the point at the wrist. And for the second part, we also took, to really assess the spine flexibility, we took the acromion point. For both points, we took at the lowest point of the bending motion, we took the distance between the point and the ground. Again, we calculated the error in centimeters between MVN and optical, and we had one final metric, the RMSE. Then we go to the full body analysis. Here we used all measured body dimensions. So, as you might know, if you fill in body height and foot length, MVN automatically scales the rest. So that's what we did. We filled in body height and foot length for the new model, either the male or the female, depending on the subject. And we filled in the same for the legacy model. Then we compared the automatically scales other body dimensions to our measured ones. And we presented this as a percentage difference. Then for the low body, we had, as I already said, the squat jump and walking at a self-selected speed. For both motions, we calculated all the joint angles. And we compared them between the OpenSim new model, so BM2, and also our legacy model. Then for the walking on self-selected speed, we also calculated the spatial temporal parameters like step width, step length, and here we used optical versus BM2 versus BM1 because we didn't need, we just could take the optical marker from the heel. Again, for both, we had the root mean squared error as a final metric. Okay, so how does the new model compare towards our legacy model and against OpenSim? Let's go into the results. Here we have first the full body analysis, shown as a scaling performance. In the graphs, on top you see all participants, in the middle it's just the male, and on the bottom one it's just the female. At the y-axis you see the percentage error between our scaled version of MVN and the measured body dimensions. On the y-axis you see all the scaled dimensions, and in blue you see legacy model, in red you see the new model. So let's go over this one by one. We start with the shoulder width, and as you can see it's kind of an equal performance. The legacy model is a bit above the zero line, the new model is a bit below the line, but on average it's 1% overestimation, 1% underestimation, so kind of equal. Then we go to the shoulder width. Here again, if you see, especially on the all participants, it's kind of equal, except that the new model, so the red bar, has a higher consistency. Then we jump a bit, we go to the hip height, and here we see that actually our legacy model was a bit more accurate than our new models. However, one thing to keep in mind here is that for the hip height you need to measure the greater trochanter, which is kind of a hard landmark to palpate. And this error we see here, the 2%, is within the range of human measurement errors. So, albeit the difference, we take it, it could be in the measurement error range. Then we go to the knee height. The knee height, again, especially on the average, they are kind of equal. The female performs a bit better than the legacy, male performs a bit worse than the legacy, but on average they are kind of similar. And then we go to the ankle, the knee height, sorry, that was the hip width. Now we go to the knee height and the ankle height. As you can see, they both improved, the knee height by 1%, the ankle height even by 10%, but of course ankle height is not that much of a distance, so 10% it's about 1 centimeter, but it's really consistent about all participants. Okay, this is of course all nice information, better most of the times, equal in some cases, but now we come to the arm dimensions. And here's where the actual improvement is. Because in the arm dimensions you have the elbow span, the wrist span and the total arm span. And as you can see, they all improved significantly. The error is reduced by over 50%. And of course this is what we expect to also impact the other upper body kinematics, like grasping, reaching motions, these kind of things. But we'll see in the next checks. So we go to the upper body hand clap motion. On the graph at the top, you see again in blue the legacy model, in red the new models. On the y-axis it's the error in the distance between the hands. And on the y-axis, on the x-axis, you see all participants, where F stands for female and M stands for male. And as you can see, our previous model, the legacy model, had an error of average 4.6 centimeters, while our new model has an error of average 5.6 centimeters. And I hear you thinking, okay, but you just said it should be better and it's 1 centimeter worse. True, I will come back to that later. Since if we check the lower graph, the clapping in front of the body, you see actually a huge improvement. We had initially an error of 14.8 centimeter for the legacy model, while now in the new models, this reduced to 8.5. This is an improvement of over 40%. Then we go, why is this the case? Why did we improve better for the clapping in front compared to clapping on top of the body? Well, here it's an interesting thing, because in Xsens Analyze, we model the shoulder as a rigid connection between the spine and the upper arm. And for the people who might know, the shoulder is quite a complex joint. So it is not just a ball and socket joint, but we also have the scapular motion, which comes into play when you elevate your arm. And that's the thing what happens here. So although we improved way on the arm dimensions, if you might have seen, were still slightly overestimated by a few centimeters. And if you then clap above your head, you can use this extra arm length to compensate for your scapular motion, which is not there. That means that actually you come closer. But then we clap in front of the body, our scapular motion is way less because we don't elevate the arms that much. In that case, as you can also see in this figure, you see that the overestimated arm length indeed makes that our arms are a bit crossing. And that's then the difference between why we improved for clapping in front so much and the improvements not that much above the head. However, we only measured on 11 subjects, as I already said. And we actually did first measurements on 20 subjects. However, in phase 1, we split it in 2 phases of measurements, and after phase 1, we had to make a slight update to the model, so we cannot use and present all the data of the 20 subjects. But what we did see is that the hand clap on top of the body over all 20 subjects was kind of similar. It even improved a bit. So what we think is that this is kind of equal performance, which will cancel out if you use enough subjects. And that's why we highly encourage you all as users to prove this and see if it's really worse or if it's actually better, what we would expect. Then we go to the other part of the upper body, the spine bending. So on the top graph, you see again the 2 models against optical. And we have here the wrist to the ground. So during the most bending, when the arms are closest to the ground, we take the distance between the wrist and the ground, and we calculate the difference with optical. So you see at the left that the models kind of perform equal, which was a bit strange in our opinion because we refined our whole spine function. So if you refine a spine function, you would expect your bending is better, you would expect your arms are closer to the ground. But then we thought, okay, but we also had a huge difference in arm dimensions. Is it that because we now have shorter arms, we do compensate by the spine, but there is less arm length, so it comes less to the ground? And indeed, if we fill in all body dimensions, it is indeed a huge improvement of 3 centimeters. So we're 3 centimeters closer to the ground with our new biomechanical models. But then still we have the arms in it, so we wanted to assess actually the performance of the spine. And for that, we did then also the acromion point to the ground, which, as you can see, indeed the new models are way better. And also in that case, if you fill in body dimensions, you still see this improvement of a few centimeters. So yes, we can still say we have an increased range of motion in our spine. Okay, the final part of the analysis is about the lower limb, lower body. Here we mainly focused on the joint angles because we didn't do huge model updates, and we actually mostly wanted to assure that the joint angles between our legacy model and the new models weren't that different. Actually, they should be kind of the same. We only changed segment lengths, and as you might know, segment lengths should not impact the joint angles. And this is indeed what we can see. We have a high correlation coefficient of 0.98 for both the gait and the squat jump between both legacy and the new biomechanical models. So that's also what you see in this table. It's not just a copy from BM1 to BM2. There are slight differences, but they're so minor that I can imagine you maybe don't even see them. And this indeed holds the same for also the squat jump. It's just to show you the table, but indeed, as already said, the correlation coefficient is really high. It's above 0.98, so they are the same. But then, of course, it's the same as legacy, but we also had the OpenSim to compare to. And here you see a moderate correlation of 0.57. And in the next slide, if you go to the gait, this is even worse, and we have a correlation of 0.31. How can we explain this? Well, as you might know, we have different models in OpenSim and in MPN. So a different rotation center of just a few millimeters could already cause a few degrees of difference. Okay, nice explanation, but how do you know for sure? And that's where, luckily, our previous colleagues already thought about by publishing the first MBN model. Because then they applied all the initial pose, so the initial calibration pose of OpenSim towards our MBN. And in that one, you can read more about it in the previous white paper, but in that one, indeed, they saw the differences were way smaller. So we do know that those differences do come from having a different model. And by showing by showing that our new models are the same as our legacy, we are sure we're still having the same good quality. And then we go to the spatial parameters. It's a huge table, I can imagine. It's a bit impressive, but on the top you see the distance in centimeters. So you have actually 3 columns, length and width for all subjects, then in the middle length and width for the females, and at the right the foot length and step width for the males specifically. On top we have the optical one in bold, which is the one we compare to. And what we see is that we have overall a gain of 0.5 centimeter, and for female it's even 1 centimeter. And we also have, if you fill in all body dimensions, indeed over all subjects, a gain of 1 centimeter, which is quite a bit in step length and step width. But then if we focus on the new models and then also fill in the body dimensions in our new models, then we see it even improves more. So if you want really accurate foot step length and step width, then fill in all body dimensions in our new biomechanical models, and you really have an improved accuracy. And then I hear you thinking again, okay, 1 centimeter better. Why is that then so much better? Because again, on these 20 subjects, which we cannot present everything from, but we knew the model did not impact that much, we see it was even better and the improvement was more than 1 centimeter. So here we are confident to say that this won't cancel out by having a lot of subjects. Okay, now we already come to the few final slides by showing some key improvements. It was a lot of information, so let's just highlight a few key improvements to wrap up. As you already know, we had a male and a female model with all different body dimensions, and indeed that was the most improvement. We have a 50% improvement in arm dimensions, which results in an overall performance improvement of clapping in front of the body of 40%.
Then we have, of course, a new refined spine model. And as you saw, it has a way more physiological behavior, but also an increased range of motion with the shoulder to ground distance increasing by 2 centimeters.
And then we have the step width again. We have a gain of 0.5 centimeters. And if you fill in all body dimensions, this is even 1 centimeter over all subjects, which is amazing in any kind of gait analysis.
And then, of course, altogether, incorporating, as we said, the subject-specific body dimensions significantly improved tracking accuracy and consistency. This is especially valuable for clinic, ergonomic, robotic application where precision is crucial. So, yeah, with the release of Biomech 2.0, we have taken a significant step forward in advancing motion capture, making it more anatomically accurate, objective, and inclusive. The new anatomy-specific model outperformed the legacy version on key dimensions, particularly in upper body kinematics and arm skilling, where precision matters. And when combined with the subject-specific body dimension, they enable assessments that are more personalized, more reliable, and physiologically faithful. While of course further development is ongoing, our focus remains advancing motion fidelity, improving physiological behavior, and broadening the depth of available data. Biomech 2.0 is more than an update. It is a new foundation built for consistency, scalability, and real-world application adaptability. It reflects our commitment to developing technology that transforms movement into meaningful and usable data for you. Whatever the application, clinical, sport, ergonomic, or robotic, we strive to give you the ability to capture, understand, and act on movement with confidence in new way and in any environment. And yes, all details and the validation metrics are available in the white paper, so feel free to reach and have a look at it. And we are really excited to see how you're going to use and apply Biomech 2.0 in real world, in research, clinical practice, and in ergonomic. Thank you all.
Okay. Thank you very much, everyone, for already sending some of the questions. So here we have Rodin and Judy. We will be able to answer all of the questions that you have about the new biomechanical model. So I see that we'll have the first question in the chat from Rebecca. Rebecca is asking, it is possible or does it make sense to analyze all the data which was collected with the previous software version in the new one?
Rebecca, for the update, you can reprocess your old data in the new software. However, it will be in the legacy model and not in the new model. To have data in the new model, you need to record new data.
Awesome. Thank you very much. The next question that we have is from Lara. Lara is asking, are these model updates available for existing Xsens users? I can answer now that it is available for all of the users who have the active SMS license. And you can download the update on our website on the page of downloads and documentation. I will be sending also the link to this page later in this chat, so you can do that. If you don't have access, then please contact your sales representative from Xsens and we'll be able to discuss the reason and find the solution. Then the question for the researchers is regarding the trunk lateral flexion and extension, what joint segment has to be considered?
Yeah, for that one, you can check the ergonomic joint angles you have in MVN. And for this specifically, I would check the pelvis T8. So that's your pelvis to the upper part of your spine, the trunk.
Yeah, makes sense. Thank you. Then Tugra has the next question. Is there no open source mockup data for MVN Xsens files, users that we can actually use for our own studies as a baseline? So to push-ups or so that we can actually see if there is a deviation from what has been measured. Is there a global data source for Xsens mockup data?
No, we don't have I don't know if there's an open source available data set with just Xsens MVN data. I'm not aware of it, no.
Yeah. Tugra, if you still would like to get an answer, then please send us a message at sales@movella or info@movella.com and we'll be able to give you an answer. Tamil is asking, this Biomech 2.0 version comes with any automated report in terms of basic and preferable parameters report?
What do you specifically mean by preferable parameters report. What kind of parameters? I mean, we do have the Xsens reports, of course, on top of MVN, like the gait report, etc. I don't know if that's meant here.
Yeah, Tamil, so if you could please send us an answer to that, and then probably we'll be able to help. If not, once again, you can just contact us at sales@movelo.com.
Definitely.
Yeah, I don't see any more questions in the chat, but actually, that's not true. There is a question coming from Asli. So, if one mentioned already, could you shortly explain the difference ergonomic angles than the usual ones?
Yeah, if you have the usual joint angles, they are between like segments, so forearm, upper arm, these kind of things. That's what we initially had, but then we knew more and more people wanting to apply it more to the ergonomic side. And in ergonomics, you have specific joint angles, not per se between two segments, but also like indeed the trunk flexion. While in the pelvis, for example, you have pelvis, L5, L3, so you have all those segments in between. So then we realized, okay, if we also give those ergonomic joint angles, which like the joint angles which are often used in ergonomics directly as output as well, that could help or benefit a lot of users. So that's why we added those as well. So it is still joint angles, but more applied to the ergonomic field. And you can like, of course, contact us, but there's also like a nice documentation on what each joint angle is and how we calculated it on the Movella base.
Yeah, thank you very much for your answer. I'm not seeing any more questions right now. So let's maybe wait for a few minutes and see if we get any more questions. And otherwise, we will be closing up the session. Let's see. I see that the response is very positive, so I would like to thank everyone for joining once again. We really enjoy talking with our clients, seeing the interest in this new biomechanical model. It is really a great feeling to see that the research that Movella is doing is really bringing forward the new innovations in biomechanics. So thank you, everyone.
Thank you. Thank you.
I'm not seeing any more questions. So everyone, if you have any questions afterwards, please contact us. And otherwise, thank you everyone for joining, and see you in the next webinar.
Bye.
Bye.
Bye-bye.